Many functions have associated with them another function called the inverse of the function. I'm going to show you how to generate the inverse of a function, and then we're going to investigate relationships between functions and their inverses. Suppose we start with this function. Now, to think about generating an inverse, we are taking the function in its manipulative form, the y equals 2x minus 3. And we're going to actually swap the role of x and y in this function. That's what inverse is all about. So to generate an inverse, we simply replace x with y and y with x. So y becomes x becomes y, and here we have the inverse of that function. Now, we wouldn't leave it like this. We would probably want to write it in some kind of function notation. So to do that, we need to first isolate y. So let's see. I'll add 3 on both sides. Then I'll divide on both sides by 2. I'm going to divide here by 2, divide here by 2. When I divide over here by 2, I have x plus 3 over 2. And when I divide on the right by 2, I have simply y. Now, normally we see the y listed on the left side of the equation, so I'll write it like that. Now, notice, first of all, that we have operations involved in this inverse function of adding and dividing. We're adding 3 here, we're dividing by 2. Look up at the original function. We're subtracting 3, we're multiplying by 2. Operations which are inverse to the ones that we saw down here. Kind of an interesting situation involving inverse functions. Now, just because we have inverse operations, though, doesn't mean that that's the way that we generate inverse functions. We generate inverse functions by saying inverse and then replace x with y and y with x and then solve for y. Now, there's a notation that indicates an inverse function, and it is this. If we want to indicate f inverse of x, the inverse function of f of x, you see, we would do it like this. F inverse of x is x plus 3 over 2. You see, this little flying negative 1 doesn't mean an exponent of negative 1 and therefore misplaced base and all of that kind of thing. This isn't an exponent at all. It is the notation for inverse function. So this is read f inverse of x. All right, now, let's look at this manipulation. Suppose we take our two functions, and I'm calling this g function, I'm calling this other function a g function. We know it to be the inverse of this f function. All right, so this is really f inverse of x. But a lot of times when functions come at us, we don't know whether we have inverses or not. And just for this process, I'm just giving it a different name. Okay, let's see what happens when we perform this calculation of the composition of functions in both ways. That is, we put g into f and f into g. Let's see. F of g of x means, let's see, f of, what is g of x? G of x is that fraction business. So it's f of the fraction. Now, f of the fraction means in the f function replace x with the fraction. So we're going to take that expression and replace x with a fraction. So we have 2 times fraction, then minus 3. 2's go out here, and we have x plus 3 minus 3. The 3's go out, and we have x. Interesting situation. Here we have, let's see, we're putting f into g. This is g of whatever f of x is. Well, f of x is this expression 2x minus 3. All right, now this says in the g function, replace x with 2x minus 3. So we're going to take this expression for the g function, replace that x with this binomial. So it'll be binomial plus 3 over 2. Binomial plus 3 over 2. Now when I drop parenthesis in the numerator, minus 3 plus 3 go out, and we have 2x over 2. Now the 2's go out, and we have x. So notice that in both directions we get x as the result of all of this. And it's simply because the inverse operations have tended to negate everything involved in our two functions. And so when we perform that composition, we're left with simply x. Now this becomes the acid test for whether or not we have inverse functions. Now we knew that we had them to begin with here, and I just wanted to show you the manipulation. But if you're asked to show that two functions are inverses of one another, then what you do is perform the composition of the two functions in both directions and verify that you get x in that calculation. Let's take a look at another situation. Suppose we start with this function and we identify first its domain and range. All right, think about domain. We've got the acceptable replacements for x. Well, let's see, all x's are okay except for that particular x that will cause this denominator to become 0. The denominator becomes 0 when x is 5, so the domain would be all real numbers except 5. X is not equal to 5. Now, the range is a little more elusive, and we haven't concentrated a great deal on identifying range, but let me just tell you this, that the range would be all real numbers. And in identifying range, we're saying, what values can y take on? That is, in this form of the function, for all of these numbers except 5 that we replace x with, what kinds of numbers come out for these fractions? You see, what values can y take on? Well, it turns out that y can take on any value in the world except 0. This fraction can never become 0. And the reason is because fractions become 0 when their numerators become 0. And this fraction doesn't have a letter which can take on a value which will cause the fraction to become 0. And so our range then would be all real numbers except 0, or we list the range as y is not equal to 0. Now let's look at the inverse. All right, to calculate an inverse, we replace x with y and y with x. The y becomes x, and the x becomes y. And now we solve for y. Now to solve for y, I would first clear the fraction by cross multiplication. Think of this as x over 1. When I go in this direction, I have x times y minus 5. So let me go ahead and with the multiplication. It's pretty simple here. X times y is xy, then x times minus 5 is minus 5x. And then on the right, 1 times 2, 2. And now I would add 5x on both sides to find xy to be equal to 5x plus 2. And now I would divide on both sides by x. So I'm dividing through by x. And when I divide here by x, I'm left with y. When I divide this term by x, I'm left with 5. When I divide here by x, I have 2 over x. Okay, so now this is our inverse function. Let me write it up here. I'd like to write it in y form. I could use that little inverse function notation that I had earlier, but I want to write it just like this because I want to identify domain and range. So you might think about this as I transfer the problem up here. Okay, so for this rascal, domain. All right, let's see, the domain, the acceptable replacements for x. Well, we can replace x with any value in the world except for that value which will cause the denominator to become 0, and that value would be 0 itself. So the domain would be all real numbers except 0, or we could simply say that x is not equal to 0. What about range? What about range? Well, let's see. What values can y take on? We have 5 plus some fraction over here. But the fraction, we know, can never become 0. It can't become 0 because there's no variable up here that will cause, there's no variable which can take on a value which will cause the numerator to become 0 and therefore the fraction to become 0. So this fraction will always have value. Might be positive, might be negative, but it'll have some value. So we're taking 5 and we're adding some value to it, you see. So this y can never become exactly 5. So the range would be all real numbers except 5. Y then is not equal to 5. Now the purpose of this little demonstration is to show you the relationship between domain and range in a function and its inverse. I want you to notice that the domain of the function corresponds with the range of its inverse. And the range of the original function is the domain of the inverse. Now, and this situation works both ways, in both directions. That is, these functions are inverses of one another. We could have started with this function. We could have said, okay, here's our original function. Now let's generate its inverse. We would be generating that. You see, and we could go through this domain and range situation in the other direction. So domain and range. All right, here's another situation. This is one of the most interesting, I think. It's the graphical relationship between functions and their inverses. All right, let's consider first of all f of x to be this and then g of x. Here is its inverse, as we have seen before. Now let's suppose I'm graphing. Now think of this as y equals 2x minus 3. I think of that as y equals the fraction. Now I generate a table of values. Okay, I pop in a few points for x and I solve for y. Now, I want you to notice what happens if I begin to generate this table of values. Suppose I let x take on the value, let's say negative 7. Now, I'm going to choose values for x that are convenient for this calculation. Suppose I choose an x of negative 7. I would have negative 7 plus 3, that's negative 4. Negative 4 over 2 is negative 2. Now let's suppose I choose an x of, let's say negative 3. That's pretty trivial. Negative 3 plus 3 is 0 in the numerator. 0 over 2 is 0. Now an x of, let's say 1. 1 plus 3, 4. 4 over 2, 2. What about an x of, let's say 5? 5 plus 3, 8. 8 over 2, 4. Now look at these two tables of values. Notice that the items in the x column here correspond precisely with the items in the y column over here. And the items in the y column here correspond with the items in the x column here. Now this is no more than an extension of that idea that the domain and ranges of these two have just swapped roles, pretty much. So in generating a graph of an inverse function, we really don't need to make that table of values. Or I should say it this way. We really don't need to evaluate the function to make the table of values. All we need to do is take this rascal right here and just flip it around like this. You see, put this x column in the y column over here, and put this y column in the x column over here, and away we go, plotting points and so forth. Here's what the graphs look like. Here's the graph of f of x, and here's the graph of g of x. Now there doesn't seem to be any discernible relationship between the two graphs, but there is really a rather intriguing one. I'm going to draw a line here just for demonstration purposes. This is the line y equals x, and it's a line that goes through the coordinate plane like this. Just kind of a 45-degree line like this. It turns out that the function and its inverse are reflections of one another in this line. That is, by reflections I mean, if we took this point and sort of attached the f function, let's just attach it right here, and then swivel it around, you see, at that point, then we would get the g function. So a reflection in the y equals x line. Interesting situation. Now, why did it do that? Why did it do that? We're swapping the roles of x's and y's. We understand that much. But why do we have this reflection in the y equals x line? Well, it's because of this. We know that on the x-axis, positive values lie out here, and negative values lie to the left. And on the y-axis, the positive values are above, and the negative values are below. Now, when we swap the roles for x's and y's, we want positive x's to swap with positive y's. You see, I mean, we want a role reversal that is true to the signs. You see, positive x's with positive y's, positive x's. Negatives with negatives in the same way. Okay, now how is that accomplished? If we had taken a graph and simply, well, think of the coordinate plane now. If I just take the coordinate plane and twist it this way, boom, then yes, I would have a situation where these positive y's would become positive x's. But the whole thing is revolving this way, or sort of twisting this way. And look at what happens to these positive y's. Boom, they become negative x's. That's not what we want. You see, so we have to find a way to swap positives for positives, and that is by doing this. Boom. When you do a swap like this, these guys swap around for those, and those guys swap around for these. You see, positive to positive, and negatives to negative. Same idea. So that's why we have that reflection in the y equals x line. Let's generate the inverse of another function. Let's start with f of x is x squared minus 2. We would write this as y equals x squared minus 2, and we find the inverse by swapping the role of x and y. Y becomes x becomes y, and now we want to solve for y. We'll add 2 on both sides, swap sides, and now if y squared is x plus 2, y then is plus or minus the square root of x plus 2. You see, by that square root property, but we kind of see algebraically here that we don't have a relationship between x and y, which is a function relationship. That is, y is not a function of x, because a single value of x can generate 2 values of y. Namely, if x is 7, we have 7 plus 2, 9. So y is plus or minus the square root of 9, plus or minus 3. So when x is 7, y is plus 3 or minus 3. Therefore, we now have this function idea. Now let's look at it graphically. We may recall that this is a parabolic curve with minus 2 on it. Means the parabola is just 2 down on the coordinate plane. So this is the graph of f of x. Now its inverse is this graph. This is the graph of its inverse. It's an inverse relationship, but that relationship is not a function relationship. Now we know it's not a function graphically because it fails a vertical line test. But you know what? We can sort of analyze this situation backwards. We can look at graphs and be able to tell whether or not inverses of those graphs are going to be functions. Here's what I'm talking about. Now let's kind of work backwards. We know that the inverse is not a function because it fails a vertical line test. But we also know the relationship between graphs of functions and graphs of inverses is that they are reflections in the y equals x line. Let's see, here's the y equals x line. You see, we have this twisting around that y equals x line. Let's twist back. From here, we twist back to that. So what I'm showing is that this vertical line test on the inverse is the same as, or corresponds with, a horizontal line test on the function itself. So if the original function fails a horizontal line test, its inverse will fail a vertical line test. On the other hand, if the original function passes a horizontal line test, then the inverse will pass a vertical line test. Let's practice the situation. Over here, we have, let's see, we have a function here. We know it's a function because it passes a vertical line test. Okay, now what about a horizontal line test? Well, we have failure of a horizontal line test, so we know that this rascal's inverse will not be a function. All right, now what about this one? Well, let's see. We are passing a horizontal line test. Do we pass it all the way down? Let's see. Sure, we pass a horizontal line test on the function, so its inverse will be a function. Here's a situation where, let's see, we are passing a horizontal line test. We pass the horizontal line test, therefore the inverse will pass a vertical line test. On this one, horizontal line test, we pass the horizontal line test. But I tricked you. This isn't a function to begin with. It fails a vertical line test to begin with. So that one's out of the discussion anyhow. Okay, so we have situations where we can identify whether or not the inverse is going to be a function by looking at the graph of the function itself. If the graph passes a horizontal line test, then the inverse will pass a vertical line test and therefore be a function. All right. Now, that situation mathematically is called one-to-one, and the graph is continually increasing or decreasing. Look at these two graphs. This one continues to decrease throughout the domain. Throughout the domain of the function, it's just decreasing all the way. This one is continually increasing throughout its domain. So no wonder you see, if it went to a certain point and it was increasing and then it began to decrease anywhere, then it would fail that horizontal line test. So it has to continually increase or continually decrease. Now this one-to-one idea is this, that it means that for every one value of x, there is one value of y. And for every one value of y, there is one value of x. That's just the nature of functions that have graphs that are continually decreasing or increasing. For every one value of x, there is one value of y. 1x, 1y, 1x, 1y, 1x, 1y, 1x, 1y. And also 1y, 1x, 1y, 1x, 1y, 1x, and so on. Okay. Now, come back to the original problem. Let's talk about domain a little bit here. We have a domain of this function which is all real numbers. Now, I wonder if there's some way that we can sort of redefine the domain of this function so that we'll have an inverse which is a function. Well, let's look at the graph for some assistance. Here's the graph of the function. It fails a horizontal line test. We know that it would pass a horizontal line test if it were continually increasing or decreasing. So, if we took out this part of the graph, if we only define the function, you see, for the values that lie out here, then it would have a graph that's continually decreasing. On the other hand, whoops, almost dropped my chalk. I juggle part-time, you know. If I take out the negative x's and just define the function from here out to the positives, then I'll have a continually increasing graph, and therefore the inverse will be a function. Well, let's do that. Let's limit the domain in some way. Let's limit the domain to positive values or 0. That is, I'm going to define this as x is greater than or equal to 0. Now, I can also go through a little discussion about range. Let me make this a little more clear by saying D for domain. The domain, x values greater than or equal to 0. Now, for range, let's look at the graph and tell. For the range, let's see what values of y happen to appear on the graph. Well, it's y values from here all the way up. So it's y values from -2 to infinity. So greater than or equal to -2. So I'm going to write y is greater than or equal to -2. Now, graphically, here's what I've got. I've limited the domain, so this part of the graph is no longer valid. It's out of here. All right, now, think about the inverse. Now, we're going to come back to the algebraic form in just a second and see what happens algebraically. But graphically, we know that if I have this as the graph of the function, then its inverse will be a reflection in the y equals x line. And if we attach it right here, if we attach the graph right here and kind of twist it around, it'll just be from here up here. So all of these values are going to be gone. Now let's see if we can't verify that idea algebraically. We know conceptually that this is what needs to happen, or this is what sort of happens with functions and their inverses graphically. But what about algebraically? Okay, we have a domain and range that we've identified for the function. We go through this inverse process. Now, we just talked about the notion that the domain of the function becomes the range of the inverse, and the range of the function becomes the domain of the inverse. The range of the function is y values greater than or equal to -2. So that means that the domain down here will need to be x values that are greater than or equal to -2. And the range down here will be y values that are, well, let's see, the domain x is greater than or equal to 0, so y would be greater than or equal to 0 down here for the inverse. All right, how does that affect this situation? Well, let's see. The domain is greater than or equal to -2. Gee, we kind of know that from the nature of the radical here. If we have the square root of x plus 2, then the only values of x that make any sense are values of x that are greater than or equal to -2. So that was kind of predetermined. The range, though, is a little bit different. Now, this says that the range needs to be y values greater than or equal to 0, but for these to be greater than or equal to 0, we would have to take out this plus or minus. We would have to take out the minus part. We would only want the principal square root. So I can just erase this, and now I have y values that are positive or 0. You see? So now I can call this the inverse function. That is, I can say that this expression is f inverse of x. And I can write it like this. Well, the calculator has some rather special capabilities when it comes to graphing functions and inverses. Let's have a look. I've already entered y equals x squared minus 2, and the expected graph looks like this. If we wanted to enter the information about drawing its inverse, we could do it like this. We could go down and actually enter those two equations that would give the inverse relationship. Now, one of them was the square root of x plus 2. I'm opening a parenthesis here, x plus 2, and close parenthesis. And let's look at these two graphs first. All right, now the other one will complete the graph of the inverse relationship, and it is the negative of the square root of x plus 2. And here's the other graph that will form that complete inverse relationship, but not an inverse function. Now, this graphing calculator, though, has a very special capability. I'm clearing this equation, and I'm going to clear this one. And I'd like to show you, here's the graph again of the original equation, or original function. The graphing calculator is capable of just constructing the graph of an inverse, whether the inverse is a function or not, all at one time. If we press clear at this point, we'll get an empty screen. And from here, we access the Draw menu. Now, to do that, press second and then the button marked Program. The second function on Program is Draw, so it's actually second, and then we're accessing Draw. Here's the Draw menu. Let's cursor down. There are a number of options here, and it's option number 8 that we want. Here's Draw Inverse. When we press Enter, here's what shows up. Draw inverse of what it's saying. Well, we want to enter y1. Now, to access y1, it's the y variables menu that we want. So press Vars and cursor right one time. It's a function, so I'll press Enter here, and then Enter again because it's y1. Now, draw inverse of y1 is what this is saying, and it's going to draw it right on top of our original graph once I press Enter. And here is that inverse relationship, which is not a function.